Hi, this is Mrs. Nearing. We're going to go through some problems involving resonance and formal charge. So this first one, we're drawing the Lewis dot structure for the nitrate ion, and we want to include any resonance structures. So we're going to follow our 5 steps for finding a Lewis structure. Step 1, count up your electrons. We've done this already. We have 5 from the nitrogen, 6 from each of the 3 oxygens. Then we're going to add 1 to our total. Why? Because this is a -1 ion. That gives us 24 electrons. Step 2, we're going to stick our least electronegative element in the middle, and we're going to connect everything else using single bonds. Step 3, I'm going to give my outer atoms an octet. Okay, that means I'm making it so that each atom has 8 electrons around it. Remember, each line here represents 2 electrons. So now each of my actions have 8. And my next step is I'm going to stop and count, see how many electrons I've used up. So I've got 8 plus 8 plus 8. I have used up 24 electrons. So I should have 24 in my picture. I've used up 24. How many are left? I've got none left to give to my nitrogen. So step 5 is I check and see, does everyone have an octet yet? And the answer is no. My nitrogen right here only has 2, 4, 6 electrons around it. It wants 8. So the only way I can do that is by making one of these oxygens share one of its pairs of electrons. And notice how there are 3 oxygens here that have some extra electrons to share. I could make any of those oxygens share an electron. So what that means, so here I'm going to draw this oxygen on the right sharing the electron, but really it's equally as likely that that oxygen on the bottom would have shared its electron, right? And then it's also equally as likely that this oxygen over here on the left would have shared its electron. So this is how you spot that you have a Lewis structure, is when you have one double bond and there's several different places where you could put that double bond. And so if someone says draw the Lewis dot structure of nitrate, what you need to do is you actually need to draw 3 structures. Why? Because the true structure of nitrate is an average of these 3 possibilities. So that can be kind of hard to picture. So one way to describe what's going on is to think about the bond order. So when we talk about bond order, we mean like a single bond, we say has a bond order of 1. So like in a, hydrogen molecule, right? This would be a bond order of 1, that single bond here. If you have 2 oxygens bonded together, that's a double bond. So we say that's a bond order of 2. If we have nitrogens bonded together, oh, I ran out of space, I'm gonna go down here. If I had nitrogens bonded together, they form a triple bond. So we'd say that's a bond order of 3. But in this molecule, the bond order, it's not 1, it's not 2, it's somewhere in between, because a 2 structure is not 1 double and 2 single bonds. It's an average of these 3 possibilities. So what it is we've got 4 bonds, right, split between 3 different locations. So what's the bond order? It's 4 divided by 3. It's 1 1/3, or if I want to write as a decimal, 1.33. That would be my bond order. Another way of thinking of it is each of these nitrogens and oxygens behaves as if it's bonded by, there's 1 bond plus 1/3 of that extra bond, right? Because it spends 1/3 of its time here, 1/3 of its time here, and 1/3 of its time here. So each of these behaves like 1 1/3 bond. And that becomes useful to know if we're comparing things like bond length. So these bonds will be shorter than a single bond. So that's a useful thing you might want to compare there. As you notice, it's shorter than a single bond, but it's going to be longer than a double bond. Why? Because it's somewhere in between. It's an averaging of these possibilities. All right, let's look at another one, SO2. So step 1, count your electrons. So S and O, they're all in column 6. So I'm going to have 6 times 3. I'm going to have 18 electrons in my picture. I'm going to put my least electronegative one in the middle. That's my sulfur. I'm going to give my outer ones an octet. Okay, then I'm going to stop and count. How many electrons have I used up? I've used up 8 plus 8. That's 16 electrons. So I've got 2 left over. Where do they go? They go on the central atom. So now I'm at step 5. I've used up all my electrons. I'm checking, does everyone have an octet? Sulfur doesn't. It's only got 2, 4, 6. Okay, it needs 2 more. Where can they come from? Well, they can come from this oxygen over here. or they could come from this oxygen over here on the left. So what do I need to do? I need to draw out both possibilities because the true structure is an averaging of these possibilities. So it's not a single bond. And sometimes use this two-sided arrow to show it's kind of like flipping back and forth between those possibilities. So these bonds, they're not single bonds, they're not double bonds, they're somewhere in between. They behave as if they are 1.5 bonds because you have 3 bonds split between 2 locations. So that's 1.5 bonds there. All right, now let's look at formal charge. So formal charge is something we can use to figure out what the best Lewis structure is when you have several possibilities that all follow the octet rule and everything. So like N2O, if you're doing the Lewis structure, you're going to add up your valence electrons and you're going to say, okay, this should have 16 electrons in it, and I want everybody to have an octet. And notice all 3 of these possibilities have 16 electrons and everyone's got an octet. So you're trying to figure out, well, which one of these structures is right, because they all seem to follow octet rule, right? They all follow our steps for Lewis structure. So we're going to find formal charge to help us figure out which structure is best. And the way that we find the formal charge is you look at the number of valence electrons that an atom would normally have minus how many dots are on that atom in the picture. Those are our lone pairs. And then minus the number of lines in the picture. Those are our bonds. So like, let's look over here at this nitrogen. Nitrogen, on the periodic table, it's in column 5, so it normally has 5 valence electrons. In this picture, there are 4 dots, and there are 2 lines. So that means my nitrogen has a formal charge of -1. This nitrogen, it normally would have 5 valence electrons. In this picture, it has no dots on my nitrogen. It has 4 lines, so 4 bonds. So it's got a formal charge of +1. And then my oxygen over here normally has 6 valence electrons. In this picture, there are 4 dots on it, 2 bonds. So it's got a formal charge of 0. Okay, so that alone doesn't really tell us much. We got to compare it to these other structures and see which formal charges are the best. And what we're looking for, the best case scenario, is that we want a formal charge to be 0 or as close to 0 as possible. And if there needs to be a negative, we want the negative to be on the most electronegative atom. Oops. So, whoops, sorry about that. Okay. All right, so we go to our next one. This nitrogen, so 5 valence. In this picture, there are 2 dots and there are 3 lines. So that gives you a formal charge of 0. So that was good. This nitrogen is normally has 5 valence. There are no dots on it, but there are 1, 2, 3, 4 lines coming out of it. So that's +1. And then your oxygen here normally has 6 valence. There are 6 dots and 1 line. So that's got a formal charge of -1. Also, if you stop and notice how when you add up the formal charges, they add up to 0. So the sum of the formal charges is going to equal the charge of the molecule or ion. So this molecule is neutral, so its formal charges are going to add up to 0. So +1 - 1, 0, that adds up to 0. Okay. Over here, nitrogen has 5 valence. There are 1, 2, 3, 4, 5, 6 dots, and then there's 1 line. So that is 5 - 7, that's -2. Oh, that doesn't look good, because we want the formal charges to be 0, but if they can't be 0, we want them to be as low as possible. So like -1 is better than -2. So let's keep going on this one. So 5 minus no dots, 4 lines, that's +1. And then this one, oxygen has 6 valence normally. There are 2 dots and there are 3 lines. So that's +1. So we're going to eliminate this one. This looks like the worst structure because, again, we want the formal charge to be 0. If they can't be 0, we want them to be as close to 0 as possible. So A and B are definitely better than C because they have lower formal charges. And then the difference between A and B is A puts the negative on our nitrogen, B puts the negative on our oxygen. And remember, our second rule is we want the negative charge to be on the most electronegative atom. So you're going to look up at your periodic table and say, who's more electronegative? Well, oxygen is. So which one has the better formal charge? That is B. So that one is the best structure, meaning that you know, when you go and you look at these molecules in real life, it's going to behave as this is a single bond and this is a triple bond. Yeah, that's how we use our formal charge. Let's look at another resonance one. So nitromethane, we're going to draw two possible structures and look at the bond order. So if we stop and add up our, let's still follow our steps for a Lewis dot structure, right? Let's add up our electrons. So we got 4 from the carbon, right? 3 from the hydrogen, 5 from the nitrogen, and then 6 plus 6, that's 12. So you've got, you know, 7, so we got 19, we got 24, right? Am I adding those up right? Okay, so I've added up my electrons. Then next step is I'm going to connect everything with single bonds. And so here I'm going to connect these like this. And you might wonder, like, why didn't I connect it this way? Well, I should know from like our octet rule that we know hydrogen only wants to have 2 electrons around it, so it's not going to want to form 2 bonds like that. So I'm going to go like this right here. So there is our initial lines we've drawn. And then I'm going to give my outer atoms an octet, which is going to be my oxygens. And my outer ones are my most electronegative ones. So I'm going to give oxygens an octet first. And then I'm going to stop and count. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used up all my electrons. But notice nitrogen doesn't have an octet yet. So it needs a double bond. It only needs one of them, though. So the possibility is that double bond could go here, or that double bond could go over here. Okay. Another thing, going back to like, how did I know the carbon's going to bond to the N versus like, why aren't there like diagonal lines going here? Remember there's this pattern from regular chemistry, honk 1, 2, 3, 4. That gives you a hint as to how many bonds these atoms typically will form. So carbon usually forms 4, nitrogen usually forms 3, oxygen usually forms 2, etc. We can see there's exceptions to this pattern, but if you're trying to get an initial structure down and you're like not sure like where the bond should go, you know, then this is usually a good pattern to just think back to. So if you have an option where nitrogen can form, you know, where carbon can form 4 bonds or one where it can form like 3 bonds, then forming 4 bonds is probably going to be the better scenario. Okay. All right. So actually notice we're breaking this pattern already in this structure. So we've got like this oxygen only has 1 bond instead of 2. This nitrogen has 4 bonds. But we know that these structures are correct. Why? Because we have the correct number of electrons and we followed the octet rule. So my structures are good. Anyways, I got a little off topic here. What's the bond order? So we got a double bond that's spending half its time over here, half its time over here. So my bond order is 1.5. So it's like in between a single bond and a double bond. Another way of thinking it, if you look over here, we've got 3 bonds split between 2 locations. So that is 1.5 is my bond order. All right. And then going down here, when you're trying to pick the best Lewis structure using formal charge, I want to point out that when you have atoms that all look the same, like these hydrogens, their bonding is the same in all of these atoms. So you just have to calculate one of them, and that's going to be true for all of them. So like for this hydrogen normally has 1 valence. In this structure, there are no dots on it, and then there's 1 line. So my hydrogen has a formal charge of 0. And that's true for all the hydrogens in all these pictures. Okay. So you don't have to like recalculate for every hydrogen. They're all the same. Okay. We want to focus on what's different, which looks like the center of this molecule is the part that's different in these structures. So as we're finding formal charge here, like if you look at this, you know, sulfur, sulfur normally has 6 valence electrons. In this structure, there are no dots on my sulfur, but there are 1, 2, 3, 4, 5 lines. So my sulfur has a formal charge of +1. Okay. I'm going to erase these ones because that got a little messy. All right. My oxygen over here normally has 6 valence. In this picture, it's got 6 dots and 2 lines, 2 bonds. So that gives it a -2 formal charge. So far the structure isn't looking great. I see lots of charges here. And then my carbon over here normally has 4 valence, there are no dots, but there are 1, 2, 3, 4, 5 lines. So my carbon's got a formal charge of -1. So I don't think A is going to be my best structure, but let's move on and look at some other ones. If we look at B, let me erase this. Okay, so if we look at B, the sulfur here in the middle normally has 6 electrons. It's got 2 dots on it in this structure, and then 1, 2, 3, 4 lines. So that's 0. So that looks good. This oxygen normally has 6, and then it's got 4 and 2. So that's got a formal charge of 0. Cool. And then this carbon is just the same as this carbon over here. We've got carbon only has 4 valence. It's got no dots. It's got 4 lines. It's got a formal charge of 0. So this looks pretty great because everybody's got a formal charge of 0. I don't really think I can get any better than that, but let's double check some things. Let's look at this oxygen here. In this structure, my oxygen normally has 6 valence. There's 6 dots. There's 1 line. So this oxygen has a formal charge of -1. So I already can see that B is a better option than C. So I'm going to eliminate this as a possibility. And then if I go down here, we just established this oxygen would have a formal charge of -1. Let's look at this carbon here. It's got no dots. It's got 5 lines. So that would be a formal charge of -1. So this also not looking great. So B is my best option here.